So we have defined the gradient of a two variable function f of xy or three variable function f of x comma y comma z. It is just a vector found by using the partial derivatives of f with respect to the variables, that is dou f by dou x, dou f by dou y, and dou f by dou z if there are three. Okay. Now we are going to see some applications of this gradient vector in finding the directional derivative of a two variable function. We have seen that the directional derivative of a two variable function is a generalization of the partial derivatives, whereas in partial derivative the increment to the value of the function is given in the direction of x-axis or y-axis, and that is we take x naught comma y naught plus s into 1 comma 0 if it is in the x direction, or s into 0 comma 1 if we are taking partial derivative in the y direction. Okay, instead of 0 1 and 1 0 you can use any unit vector u and calculate a derivative. Such a derivative is called the directional derivative. And in order to calculate the direction, we have seen how to calculate the directional derivative for a two variable function or three variable function. Also you can do this same. That is, we use a definition to calculate the directional derivative, and it can be calculated using the one variable function g of s, where g of s is the first function obtained. That is, this you take this function as g of s. Then what happens is, if you take s is equal to 0, then this first expression will become the second expression. So you can say that this limit is nothing but limit of g of s minus g of 0 divided by s. And if you recall the one variable definition of derivatives, this is nothing but limit s tends to 0, g of 0 plus s minus g of 0 divided by s. That gives you the value of g dash at 0. G dash 0, where g dash of s, g of s is equal to f of x naught plus su1 comma y naught plus su2, which is a function of s. So the same idea will be used in deriving an expression for the directional derivative in terms of the gradient vector. So for a three variable function, that it is du f at x naught y naught z naught is equal to derivative of f of x naught plus su1 y naught plus su2 and z naught plus su3 evaluated at s is equal to 0. Okay, and we are going to derive an expression for duf using the gradient vector. Okay, it's easy. So the directional derivative, by definition, it is duf at x naught y naught is equal to the derivative of g of s. What is g of s? It is the first function, that is f of x naught plus su1 comma y naught plus su2. Okay, with respect to s, this has to be evaluated at s is equal to 0. Directional derivative at x naught y naught, which is the limit of this expression. I am treating it as a one variable function because these expressions are constant, x naught, u1, etc. are constant. So it becomes g of 0 plus s minus g of 0 divided by s, as s tends to 0. And this is nothing but g dash at 0, or you can say that this is d by ds of g of s at s equal to 0, evaluated at s is equal to 0. Now, how do we derive this is like this? So you know that this limit can be written as d by ds of f of x naught plus s into u1 comma y naught plus s into u2, where u1 and u2 are the coordinates of the unit vector u. Always remember that u must be a unit vector. Okay, I'm going to call this expression x naught plus s u1 as x small x, and this expression as small y. Now what happens is, your function f is now a function of x and y, and where this x is some function of a new variable s, and y is also a function of the variable s. So d by ds you can calculate using this expression, that is d by ds of f of x comma y, where x and y are functions of s. So now using chain rule, d by ds of this particular function can be written as this dou f by dou x, dou f by dou x into dx by ds, that is this one, f to x and x to s, plus dou f by dou y into dy by ds. Okay, so this is nothing but the partial derivative fx into, what is dx by ds? This expression I am calling as x, right? X is this x naught plus su1. So what is dx by ds? Dx by ds is nothing but the derivative of x naught is a constant. X naught is a constant, so derivative is 0 plus u1 is a constant into s derivative with respect to s is 1. So dx by ds is u1. Similarly, dy by ds, if you calculate, it is going to be u2. Okay, so I can call this as fx comma fy, which is a vector dot product with the u1 comma u2. Okay, now what is this? This is the partial derivative of f with respect to x and y as it taken as a vector. That is our gradient function, right? So it is del f dot what is u1 u2? u1 u2 is the unit vector u. So del f dot u cap. So you can say that the partial derivative, not partial derivative, the directional derivative du at f du f at x naught comma y naught is nothing but the directional derivative evaluated at x naught comma y naught dot product with the unit vector u cap. So this is an easy formula for finding the directional derivative. In the slides, there is a small mistake. It is there should be dou f by dou x because f is a function of x as well as y. So it should be partial derivative. This is a partial derivative. It's also a partial derivative. So fx and fy. You can say that even in the three variable case, if you substitute this x naught plus su1 as x and y naught plus su2 as y and z naught plus su3 as z, then also you can derive that duf at the point is equal to fx comma fy comma fz, which is gradient of f dot product with u1 u2 u3, which is u cap. Okay, and the same problem which we evaluated using the definition has been evaluated here. So but in order to apply this method, you must remember that the function should be having continuous partial derivatives. Now we have seen that fx of x naught y naught, fx at x naught y naught gives the slope of the surface in the x direction, and fy of x naught y naught gives the slope of the surface at the point x naught y naught in the y direction. Instead of that, since we are measuring the rate of change of the function in any given direction u, this du f at x naught y naught is a generalization of the partial derivatives, and therefore it gives du f at x naught y naught gives the rate of change of the function in u direction, or it gives the slope of the surface in the u direction, where u can be any direction in the domain plane. So in the domain plane, you fix any direction u instead of the, if you want the x direction or y direction, partial derivatives will do. And if you want to have the slope in the u direction, where u is a inclined direction, then what you have to do is you find du f at x naught y naught. That will be giving you the slope in this direction, u direction. Okay. Since the directional derivatives are giving the slopes in any direction, we are interested in finding the slope of the surface in, or the highest value of the slope and the lowest value of the slope of the surface. Okay, at a particular fixed point. So we are going to see the slopes of the surface and at in which direction the slope will be the highest, lowest, etc. 0. Okay, so it's easy. So we know that du cap f is equal to del f dot u cap, right? And so it's a dot product, and you know that a bar dot b bar is equal to mod a mod b cos theta. What is cos theta? Theta is the angle between these two vectors del f and u cap. So if this is the del f direction and this is the u cap direction, then the angle between them is theta. Okay, so you know that du f is equal to mod del f dot or mod u cap into cos theta, but mod u cap is always 1 because it's a unit vector, so it just becomes mod del f into cos theta. Okay, now the question is, when du cap f will be maximum if you take u cap in which direction, this du cap f will be having a maximum value. So the maximum value depends on this cos theta value, because when theta is equal to, cos theta value always lies between -1 and +1. So suppose theta equal to 0, then what happens is this del f and u cap, del f is this and u cap is also in the same direction because the angle between them is theta equal to 0. In that case, what happens is du f will be equal to cos theta equal to 1, right? So it will be just mod del f, and you know that this du cap f is always less than or equal to, this cos theta will be between -1 and +1. So the minimum value of du cap f is equal to minus of mod del f, and the maximum value will be mod del f. Okay, so when du cap f becomes of maximum value, that is when that happens when cos theta is equal to 1 or theta equal to 0. So that means, so when theta equal to 0, du cap f is equal to mod del f, which is the maximum value that du cap f can take. Du cap f can assume. Okay. Now suppose theta is equal to say pi, then what happens is cos theta become cos pi, and cos pi is -1, right? So then du cap f is equal to minus of mod del f, and this is the minimum value. This is the minimum value that du f can take. Or you can say that the slope will be maximum in the direction when u cap is equal to same as direction of del f. Okay, so the maximum slope happens when you take the directional derivative in the direction of del f, and the minimum slope occurs when you take the slope in the direction of u cap, which where u cap is the negative vector of del f, because the angle should be pi means this should be del f, and your angle should be pi means 180 degree, right? So it should be opposite. U cap should be opposite to the direction of this del f. And what happens if theta is equal to pi by 2? When theta equal to pi by 2, cos pi by 2 will become 0, and du cap f in that situation it becomes 0. So what happens is, if the gradient direction is this, then if you just take the perpendicular direction to the gradient vector, that is, this is del f direction, and if you take u cap in the at an angle 90 degree to del f, then what happens is this vector, since it is perpendicular to the direction of del f, the slope will be 0. That means there will not be any ascent or descent if you go perpendicular to the direction of this del f. So that's how it helps in the geometry of surfaces, identifying the geometry of surfaces. So let f be a function of 2 variables or 3 variables, and you take a fixed point x0, y0, and suppose that the function is differentiable. Then if del f is equal to 0, then all the directional derivative are 0. And if del f is not equal to 0 at p, of course del f is equal to 0 means 0 vectors, and all the partial derivatives fx, xy, fz are becoming 0. If del f is not equal to 0, then you can talk about the uh, maximum slope, minimum slope. Then the derivative in the direction of del f, that is u cap, is taken as the unit vector in the direction of del f, that will have the largest value, and the largest value will be the length of del f, or and the minimum slope direction is going to be the opposite direction. That is, if you take u as minus of the left direction, opposite to the left direction. So this is an example to find the maximum value of the directional derivative at the point -2, 0, and the unit vector in the direction in which maximum value occurs. So what happens is, here it's a 2 variable function. So the maximum value of the directional derivative will be del f. And what is del f? Mod del f. So del f is this 2x into e raised to y I plus x square into e raised to y j. So del f at -2, 0 is going to be obtained by substituting x equal to -2 and y equal to 0 at this point -2, 0. So it is -4i plus 4j. So the maximum value is going to be its length, so root of 32. Now the direction in which the maximum derivative occurs will be the direction of del f, and u cap you have to take as a unit vector. So the unit vector in the direction of -4i plus 4j is going to be obtained by dividing del f by its length. So you divide this vector by its length is 4 by root 2, right? So u cap you have to take the unit vector in the direction of del f, which is a vector divided by its length. So -1 by root 2 I plus 1 by root 2 j. And the minimum slope occurs in the direction of minus of del f. That is, it will be plus 1 by root 2 I minus 1 by root 2 j. Okay. So this is how one can use del f in identifying the highest slope, lowest slope, etc.